Welcome, Physics 30s. Today we talk about probably my favorite lesson in Unit 4. It's Young's double slit experiment. And what Young did with this slit experiment is to figure out the wavelength of light. Now just think about that for a second, the wavelength of light. Like, we all see light, we all experience light, at least in the visible spectrum. We experience it in other spectrums as well, like UV and IR. But do you ever really see a wave of light so that you can pick up on the wavelength? Not at all, right? And you can't slow it down so it's more visible. You can't see individual waves. You can't do anything like that. So how Young figured this out is actually fairly simple, but also super genius. Like, this is a cool lesson. The other neat thing about this is also the last lesson of Unit 4, believe it or not. So we're doing it. We're getting there, everybody. We're doing it. So let's jump in, and we start off with a bit of review, but let's jump in and let's check out Young's double slit experiment. So first and foremost, we've got the diffraction of light. So this diffraction of light, this is conclusive evidence that light behaves like a wave, right? So if you remember diffraction, first and foremost, I guess that's the spreading out of a wave, sort of filling the space as a wave passes by a corner or through an opening, right? So through a slit is what we're looking at. So some things that you might remember. This first diagram up top here, so this diagram that I'm circling right here, those waves have the same wavelength, but one's passing through a large opening or a large slit, and the other one a smaller opening or smaller slit. Which one is diffracting or bending more? The smaller one. So smaller opening means larger diffraction. Cool. Smaller opening equals larger diffraction. That's something that we need to know about. The diagram that's directly below that, so the idea of a diffraction grating is just a thing with a whole bunch of little tiny openings or a whole bunch of little tiny slits. The one that I used to create the picture on the bottom right was, let's see, 530 openings per millimeter. So a ridiculously small, 530 in one single opening. So very, very, very small openings, but it produces the same effect. And then what do you notice with this? So if the light was passing straight through, I missed, the light was passing straight through and going out to here, so that's light passing straight through. What diffracts more, longer wavelengths or shorter wavelengths? And if you said longer wavelengths, because red has a longer wavelength, and look how much it's bent, whereas violet has a shorter wavelength and it's bent significantly less. So there's the violet, there's the red. So in summary, we've got smaller openings mean bigger diffraction, and we've got longer wavelength means more diffraction. So again, smaller openings and longer wavelengths. Now this is actually the picture on the other side. I added this in. It's a little bit too soon for this, but this is actually diffraction. These are some of my laser pointers, and each one of the ticks is 10 centimeters. So between each of the ticks is 10 centimeters. So through diffraction grating, that's the same distance from the board. I've got my central bright spot, and we'll talk about these in a second. So there's a central bright spot for both the blue and the green. And then my first order bright spot are, let's see, a little less than 30 centimeters away. But if I look at the green one, 1, 2, 3, it looks like it's about 40 centimeters away. And that again goes and talks to us that and tells us that short wavelengths diffract more, or sorry, less than long wavelengths. I'm confusing myself here. But short diffract less than long. Cool. So think about this for a second. We've got AM and FM radio stations. We have talked about these before. AM has lower frequency radio waves, and FM has higher frequency radio waves. I'm going to grab a different color, make it a little bit easier for people to see, I think. So who would be, or what would you have to be happier listening to your radio in this house? Would you rather have AM or rather have FM for a clearer signal? If you're saying AM, because remember, low frequency means big wavelength, or small frequency, big wavelength. It's that inverse relationship, and that relationship comes from, I guess not C necessarily, V is equal to frequency times wavelength. So the smaller the frequency, the longer or the bigger the wavelength. And the bigger the wavelength, the more it bends as it goes around an opening. Whereas FM, maybe I'll do FM in green, bends significantly less as it goes past that hill or that opening. Cool. Okay, so next thing, and I kind of already showed you this before, the interference of light. So when I go through and I talk about interference of light, this is another piece of evidence that light is definitely 100% behaving like a wave. We've seen some of this in Physics 20 where we've had loud versus quiet. I think I've probably even showed you the bright versus dark spots with the laser pointers. But essentially what we've got is I've got this source of light, and that's the waves that are coming through here. It's passing through a single slit. It is diffracting a little bit, and then it's passing through individual slits, so other waves that are essentially coming through here. And we really want to focus on this piece, the second thing that it's hitting. And then they start to spread out, right? So it diffracts from the first one, spreads out in that nice circular pattern, diffracts from the second one, spreads out in that nice circular pattern. And where we have crests with crests and troughs with troughs, we have constructive interference. So that's all along this path right here, crest with crest, crest with crest, and we end up with a bright patch along that path because we've got constant constructive interference. And every time we see that, we see constant constructive interference, we see these bright spots. Cool. Where I have destructive interference, that's where a crest meets a trough, they cancel each other out. The waves cancel each other out, and that's where we end up with these dark spots. So dark spot, dark spot, dark spot. Cool. Do particles cancel each other out like that? No. So again, very, very, very conclusive evidence that light is definitely behaving like a wave. Cool. So Young's double slit experiment. Like, yeah, this is cool, but how does this get us the wavelength of light? We're not quite there yet. So there's a couple things that I'd like you to watch here. Put the video on pause and check out. I do have the links there, but it might be annoying to try and type those in. If you just Google search the original double slit experiment by Veritasium, and then shortly after the single photon interference by Veritasium. Now you can watch that whole one if you want to, but you don't necessarily have to. If you watch up to about 2 minutes, I think it's actually like 1:56 or something like that. It'll get you what you need. Fantastic animations of what exactly is going on with the interference and the double slit experiment. So anyways, you can put the video on pause, go check those out. I think about 10 minutes or so of videos there. Okay, go for it. Alrighty, so pretty cool, right? And I really like with this first video, I really like how he's in the pond and like showing the different waves and how they interfere with each other. Does a fantastic job of that. The second one, the single photon interference, when you break it down and you just look at those individual photons, the real big key with that is, and the huge idea with that is, the path differences is kind of what we're looking at, right? So if they're both, the black and the blue wave are both in phase and they're starting from the same position, obviously we're going to get constructive interference, crests with crests and troughs with troughs. But if they're shifted, right, and they're shifted by half a wavelength, so right now the blue is starting half a wavelength further back than the black, and now we've got crest and trough, and crest and trough and crest and trough. We've got totally destructive interference. If I shift that blue length a little bit more, the blue wave, sorry, a little bit more, now we've got totally constructive interference. And notice now that we're shifted by one full wavelength. So when we're shifted by whole number multiples of the wavelength, we get constructive interference, and when we're shifted by half multiples of the wavelength, it is destructive interference. Cool. This is what leads us to this interference pattern. So we've got a central maxima, that's the blue one in the middle there, and then we've got first order maxima, which are N1, and they go on either side, and second order maxima, N2. Again, they go on either side, and realistically, you might have like N3, N4, stuff like that. Eventually, they get darker and darker and darker the further you go. So again, these are called maxima, so central max. You got your first order maxima, your second order maximum, and so on, and so on, and so on. Cool. Very, very good. So again, I've got these same pictures that we've looked at, the green laser pointer and the blue laser pointer. And with each of these, let's see, green, I've got my central maxima here and my first order maxima here and here. And same thing with the blue, I've got my central, and then I've got my, that's not anything, my first order and my first order maxima there. So that's what it would actually look like on the screen. Again, we've got these diffraction gratings. So the one that I used for this was 530 slits per millimeter. They are essentially little tiny openings that the light passes through and interferes with itself and produces these patterns, which is pretty cool. Now, essentially what we've done here, when we're predicting these maxima and minima, we're looking at this as if it's a side view. So I've got the laser pointer here, I've got my screen over here, and the laser pointer, it's going to send its central maxima straight through the diffraction grating. So the diffraction grating, maybe I'll put in green, just because, why not? And actually, you know, I switch some of these colors up. So there's the laser pointer shooting a red laser through the green diffraction grating, and it's showing up on the screen. What's happening with this is if we were to take a side view, it would look like I've got my first order maxima there, my second order maxima there, and I would have the same thing on the other side as well. We're just kind of ignoring this top part. We're only looking at part of it, and we're really only looking at what is going on the screen with that central and our first order and second order maxima for this one. So going through the slits, it diffracts, it produces our pattern, and yeah, it's two circular wave fronts, right? But that's not really what we're concerned about here. We're concerned about those areas of pure constructive and pure destructive interference. So constructive, 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 and then the middle, destructive. Cool. So that's the diagram that we want to look at. And again, when we go through the video, I think did a better job. The second video did a better job describing this. But from the two slits, they have to, so they're in phase, they have to travel the exact same length to get there, or the exact same path to get there. And if they travel the exact same path, they're going to arrive in phase, they're going to arrive as crests with crests and troughs with troughs. That's going to be constructive interference. So same distance, obviously constructive interference. If I go to my first order minima, so minima, when I look at this, you could probably guess what this path difference is. The path difference is 0.5 of a wavelength. And what happened when things were shifted by, let's draw it out again here. What happened when things were shifted by half of a wavelength? So they're traveling the exact same length. If we shift by half of a wavelength, not at all what I wanted, shift by half of a wavelength, all of a sudden it is total destructive, and that's why we have nothing there. Cool, so one just has to travel a little bit further. The next one is my first order maxima that I want to talk about. And again, you could probably guess what the path difference is, because if I, not at all what I wanted, if I shift by half of a wavelength, it was destructive. What if I shift by a whole wavelength? Where's the mouse pointer? There we go. If I shift by a whole wavelength, we're back to being constructive. The pictures are getting worse, but the idea is still there. Cool. So it turns out anytime the path difference is a whole number multiple of the wavelength, we've got constructive interference. Anytime it's not a whole number multiple of the wavelength, we've got destructive interference. So again, when the path difference, delta D, is equal to a whole number multiple of the wavelength, it's constructive, and you see stuff, right? You get a maxima. Awesome, perfect. Okay, It still hasn't really told us how we get the wavelength of light yet, but we're getting there. We are getting there. So you might remember stuff from this. You can try this one out for a second if you want to. Put the video on pause. But you might remember stuff like this from Physics 20. So I've got source 1, source 2. They're giving off waves that have a wavelength of 80 centimeters. Can we predict whether point P is going to be a maxima or minima? Go ahead, put the video on pause right now and do it. Alrighty, so you had an opportunity to think about it. Again, the whole key is talking about that path difference. So one's got to go 160, one's got to go 120. That means the difference between source 1 to point P and source 2, well, that's 40 centimeters. One's got to go 40 centimeters longer. Now, is that a whole number multiple of the wavelength? So let's see, n times 80 centimeters, and can we get n to be a whole number and multiply it to get 40? I don't think we can, right? So the path difference is not a whole number times 80, it's 0.5 times 80. That sounds like it's going to be a minimum or destructive interference, because the path difference is half of a wavelength. Ooh, no, destructive. Okay, so again, we still haven't really seen how Young has figured this out. But here we are. So things that we look at here, I'm going to highlight in green and maybe another color. So if we can see this triangle right here that I'm highlighting in green, this triangle right here, highlighted in green, this makes a like or similar triangle to the one that I'm going to highlight in blue. So the 90-degree triangle, they're both 90-degree triangles, and they're both similar triangles or like triangles. What that means is theta for the big triangle, that's this one, is equal to theta for the small triangle, that's this one. So the angle is exactly the same. Now that small triangle that we've got there, D, the letter D, the distance between the opening and the slits, well, that's tiny. Remember, 530 openings per millimeter? That's tiny. You can't really measure that very well. And n times the wavelength. Well, wavelength, we're typically dealing with nanometers. That's tiny, not easy to measure, and definitely not easy to see when we're talking about light. So that triangle that's got the wavelength in it, difficult to deal with. But let's see, let's focus on this big green triangle a little bit. So if this is I'm going to clean this up a whole bunch right now. Get rid of all this writing. So if this is my two slits from my diffraction grating, and we're measuring from my diffraction grating to the screen, could we easily measure from the diffraction grating to the screen? I have one set up behind me right now from when I was taking those photos. The diffraction grating's on the lab stand. My whiteboard is right there. I could take a tape measure, and I could measure that no problem. Cool. Could we, on those pictures that I showed you of it, could we measure this distance from our central maxima to our first order maxima? Absolutely we could, yeah. So all of a sudden we've got two measurements here, Could we figure out that angle from those two measurements? Could we figure out theta? Absolutely. And if that theta is the same as that theta, all of a sudden we have that particular one in the smaller triangle. Now, if we know how many slits per millimeter, could we actually, I know it's not the easiest thing, like you can't take a ruler and see it, but could we figure out the distance between the slits? Absolutely we could. So now all of a sudden, we've got an angle, we've got the distance between the slits. Let me erase this. Getting pretty sloppy here. We've got an angle. We've got the distance between the slits. We know this is a right angle triangle. So could I figure out that side of the right angle triangle? Absolutely. And when we do that, we're actually going through and we're building this formula. So this is just sort of the math on how we build it. It turns into that one. This one is on your data booklet. This is a fantastic formula. This formula always works. It is awesome. That is a great formula. And look at that. Our wavelength is right there. Young figured out the wavelength of light. Cool. Very, very, very cool. Very impressive. Okay, the other formula is still okay, but it only works for small angles. which makes it kind of annoying, right? So you have to memorize that you can only use this one for small angles. That being said, you can usually just get away with using the other one. So I use this formula for pretty much everything. This one, kind of ignore. I need to teach it to you. You need to learn it, but you can probably ignore it for the most part. So wavelength is equal to XD over NL. So lots going on with this. D, the distance between the slits. L is the length that the light has to travel. So that's from the slits over to the screen. So in my case, it was the whiteboard. X is the distance between the maxima. So depending on what maxima you're using, if we're using n is equal to 2, let's see here. If we're using n is equal to 2, you would use this whole x value up here. If we're using n is equal to 1, this is going to be x when n is equal to 1. Cool, so x changes depending on which value you are actually using. Cool, and if you want a challenge, and this is actually quite a challenge, see if you can figure out why. It's mostly for your Math 30 and 31 people out there. See if you can figure out why this only works for angles less than 10 degrees. Cool, okay, let's jump in. We got an example here, seeing how these formulas and these ideas work together. So I'm gonna get a little bit nicer of a felt pen. I think that's a little bit better. So we have 550 nanometer light. Sounds like our wavelength. Excellent. It's shone through a diffraction grating, which has 700 slits per millimeter. So 700 little openings per millimeter. Cool. We'll have to deal with that. So it says on a screen. The distance between the maxima is 26 centimeters. So distance between the maxima, that is, excuse me, x. And we want to determine the distance to the screen. So I think what we're actually looking for in this case is L. Now something that's going to help us out big time with this is a diagram that actually looks good and makes sense. So I've got slit 1 and I've got slit 1, slit 2. Those are my two openings. Now it looks like the light is always coming from directly in between. We've got our central maxima that is going straight across and hitting our screen and creating our central maxima. Nice. We've got our first order maxima coming here and it's making n is equal to 1. We also have, so realistically, we have it coming down here and we have n, oops, should write it down there, is equal to 2 as well. So let's first and foremost, let's deal with this x. It says the distance between the maxima is 26 centimeters. That means between central and n is equal to 1 is 26. Oops. Go back there. So x, it's black all of a sudden. 26 centimeters. And then that means also between there and there, that's equal to 26 centimeters. Now I've already labeled this as x because, well, why would we want to do 52 when we can just keep it simple and draw it like this? Okay, this is going to be annoying because it'll go back to being blue. So that was S2. Okay, nice. We've got our theta showing up in there, so we've got our angle showing up right there. We know that these, even though it's kind of messy, this should be at a right angle right there. And finally, L is the distance between our screen and the diffraction grating. So labeled diagram to help us out there. Cool. So let's deal with that diffraction grating. 700 slits per millimeter. What that's going to give us is actually D in our formulas. So the distance between the slits or the distance between the openings. We just need to figure that out and kind of convert that. So D is the distance between slits. I've got 700 slits per millimeter. So let's see, 700 openings per 1 millimeter. That's realistically equal to 700 openings for every 0.001 meters, right? So all I did was convert millimeters to meters because I want everything in meters. Cool. So that's fine. I don't really want the slits per meter though. What I really want is the meters per slit. So what I'm going to do with this is I'm just going to take the inverse, to be honest. So D is going to be equal to 0.001 meters for every 700 openings. And let's see, we got to plug that into a calculator here. So you go ahead and do that. I'll do the same thing. And it looks like it's going to be 1.42857 times 10 to the negative 6 meters. So we got D. Perfect. And hopefully people agree. Hopefully you see how we did that. It's just kind of our definition. It's how far apart those slits are. So I take the total distance and divide it by the number of slits, and I get how far apart they are. Nice. Okay. So we have two formulas. We got lambda is equal to xd over nl, and we've got lambda is equal to d sine theta over n. So right off the bat, it might look like, oops, lambda is equal to xd over nl is our formula, because we've got lambda, we've got x, we just figured out d, we know n, we're looking for l, so that looks reasonable, but this is only for less than 10 degrees. Do we know if that angle is 10 degrees or not? No, so we should probably check and figure out whether it's 10 degrees to see if we can use that. And we should always check to see if it's 10 degrees. So I don't have two sides of the right angle triangle. I think we might need to use that other formula in order to figure that out. So let's go ahead and let's find the angle. So I'm just going to, that is not at all a pen. So find theta. Cool, so I think I can use the other formula. Lambda is equal to d sine theta over n. And if we're using n is equal to 1, oh man, does that make life easy? That just makes life so easy. So let's rearrange. Let's go sine theta, and actually, well, you know what, I'll do it in 2 steps. Sine theta is going to be equal to theta times n divided by d. And I don't really want sine theta, I kind of want theta. So let's say theta is equal to inverse sine of lambda times n over d. Shoot, drop my felt pen. And all we got to do is plug some numbers. So go ahead and do that now. So that's inverse sine of, what was it there? 550 nanometers. Let's change that into meters. So times 10 to the negative 9 meters. Times n, which was -1. So I'm going to leave that out, to be totally honest with you. Not -1, sorry, just 1. I'm going to leave that out. And I don't know why this isn't working out so hot for me. So 550 times 10 to the negative 9 meters. And then we're going to divide that by, we just figured it out, 1.4285 times 10 to the negative 6 meters. So that's our distance between the slits. And plug that in, and what do you end up with? Don't forget, by the way, make sure that you are in degree mode for this. I end up with 22.644 degrees. That's a bit of an issue, because that means we cannot use lambda is equal to xd over nl. There's got to be another way, though. There's got to be another way. So let's go back up to here and let's check this out. So it's a right angle triangle. I just figured out that this is 22.6 degrees, roughly. I know the opposite side, and I'm looking for the adjacent side. Hold on. We can do this. Know the opposite, looking for the adjacent. We have the angle. Let's just use tan function. Easy peasy. This is getting a little bit messy. I am so sorry about this organization. This is miserable. Really, really bad. So let's find L, and all we're going to do is we're going to say tan theta is equal to the opposite over adjacent. So let's see, the opposite in this case is x, and the adjacent is L. So opposite is x, and adjacent is L. Cool, from there, well, I just got to rearrange. L is equal to x over tan theta. So x was 20, what was it? 26 centimeters or 0.26 meters. And tan theta is the tangent of 22.644 degrees. Awesome. Take a second to plug that in. And we end up with 62 centimeters, or I guess realistically you would have got 0.62 meters, but 62 centimeters, the same thing. Awesome. So I hope that makes sense despite my terrible, 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 horrible organization that you've got here. And what I really like about this particular example here is the idea that yes, we have lambda is equal to xd over nl, but that formula is kind of useless. You have to check the angle anyways. Lots of times, most of the time, the angle is more than 10 degrees. So use something else. Use some basic trig, right? It's a right angle triangle. You can use some basic trig, or use the lambda is equal to d sine theta over n, or a combination of the two. Cool. So there's our first example with that. And last couple things to talk about is just some ideas of light, some things that light does that, well, particles don't. So this is definitely light behaving like a wave. First off, dispersion of light. Dispersion means separating or spreading out, right? So dispersion of light is the spreading out of light, and it's in particular into its individual wavelengths. This is how rainbows form. Which is pretty cool. There's two different ways to do this. You can use a prism or you can use a diffraction grating. A prism is realistically just a chunk of glass. Sometimes around your house you can see rainbows coming through chunks of glass. I've got this thing hanging in my window that's almost looks like an Easter egg, but there's like a billion little... This is actually not a bad drawing. A billion little surfaces, and it casts rainbows all over my kitchen. That's a terrible drawing now that I look at it closer. I thought it was good. It's not good. But yeah, so through a prism is based on refraction, and through a diffraction grating is obviously based on diffraction, and some wavelengths refract more than others, some wavelengths diffract more than others. So dispersion using a prism. Do you remember which ones bend the most and which ones bend the least? Which wavelength? So is it red or is it violet? Take a second to think about that. So if you're saying that the violet bends the most, absolutely 100%, you are spot on. Violet or shorter wavelengths bend the most, and longer wavelengths like red bend the least. And again, if they're bending at different rates, that's going to separate them into their individual components. So again, important thing to remember from this, refraction. When we're talking refraction, the short wavelengths bend more. What about diffraction gratings? We talked about this at the beginning, right? So in diffraction gratings, we've got the same size opening for each of these, and we know that the smaller the opening, the more diffraction, but these, excuse me, these are the same size. So what about the wavelengths? You got long wavelength versus short wavelength. If you're saying to yourself, oh yeah, the short wavelength diffracts less, the long wavelength diffracts more, you're spot on, which is kind of the opposite of refraction, right? Opposite of refraction. So the patterns that we see kind of look like this one, where I've got the longest wavelength, you cannot see black on black. I've got the longest wavelengths, the blue and the purple, diffracting the least, and the shortest wavelengths, I said that totally backwards. I'm exhausted here. Sorry, folks. The blue and the purple, the shortest wavelengths, diffracting the least. The red, the longest wavelength, diffracting the most. Oh boy. Here's your summary for this. They're opposite patterns. Refraction, red bends the least. Diffraction, violet bends the least. And then opposite for the, the violet, right? So violet bends more versus red bends more. Opposite. Now, honestly, I'm doing a horrible job explaining this right now because it's home time and I'm tired. But If you can remember one, you can remember the other because they're opposites. So typically I remember diffraction, where violet bends the least and red bends the most, because that's what we did in physics 20 and we're doing again here. And then I just remember refraction is opposite. Cool. Last big thing to talk about is polarization. So, oh, and by the way, when I go back to this, only waves do this, right? So particles do not spread apart and they do not disperse. So this is evidence again for light behaving like a wave. Polarization, more evidence for light behaving like a wave. So light typically oscillates on all planes. So you know you got your, I don't know if I'll be able to draw this. So yeah, that's not going to work out. But you know that your electric field is perpendicular to your changing magnetic field, which is perpendicular velocity. I can draw that one. Realistically, though, it's not always neat like we've got drawn. It's kind of more of a scramble where they're all over the place in a whole bunch of different planes, all essentially at the same time. So what polarization does is it's kind of like those diffraction gratings, but on a much, much, much smaller level where it filters, it's so small, it filters the vibrations so that they're only in one plane. So if I had this one, it's filtering out everything except for the vertical. So here's my mixed wavelength, all kinds of stuff going on. It's all over the place in tons of different planes. It's filtering everything except for the light that is in the vertical plane. So then only the stuff that the vertical plane goes through. If I put another one, now this one is horizontal on the right-hand side, so I've already filtered out all the horizontal stuff. Now I'm filtering out the vertical. Nothing's going to get through. So if you have two pairs of these lenses or these filters, you can totally block out all light. Now, lots of you might have polarized sunglasses. I have a couple pairs of polarized sunglasses. They're pretty neat because they really, really, really reduce glare, right? So the light is, you know, being polarized on the horizontal planes, causing horrible reflections. You don't really want that. You want to reduce glare, so you wear your polarizing glasses and you only get one plane of that light. Now, if you take two pairs of polarized glasses and you put one pair like this, those are glasses, trust me, and then you put another pair like this, see what comes through this particular lens right here. It's going to be pretty much black, which is pretty neat, right? That's a good way that you can tell because no light will go through. One's polarizing them vertically, the other's polarizing horizontally, nothing comes through. So cutting glare, this is essentially what we look like or what things look like. So with a polarized lens, tons of glare. You can't really see what's going on inside the car. Without a polarized lens, tons of glare. With a polarized lens, you cut the glare, you can see inside of cars. Lots of cops like to have these polarized glasses because then they can see through the glare. They can see what people are doing if they're texting and other dangerous things inside the car. Lots of fishermen also like this. In particular, fly fishermen, where you actually have to aim for the fish and try and lure the fish onto your hook, rather than just like cast and reeling it in. We're just kind of hoping to get a fish. Again, polarized light, you can actually see through the water a bit more and see the fish. Cool. Again, this is conclusive evidence that light is behaving like a wave because you cannot polarize particles. Particles either do go through the openings or they do not, but they don't get polarized in terms of a single plane. Cool. My apologies for the last little bit of that lesson. I kind of rambled a little bit there. I think it's time for me to go home and get some rest. Good talking to you, Physics 30s. You're doing great here. We are done Unit 4, which is pretty exciting. Pretty impressive. We'll be moving on to Unit 5 soon enough, where things start to get pretty interesting. Anyways, that's it for now. I will talk to you again soon. Bye-bye, Physics 30s.